during first year, I was studying waves at first year of university, and I noticed that the wave equation could be analogous to the equation E equals mc squared. And I just became obsessed with this kind of notion, looking for potential hidden ways to look at physics alongside learning it traditionally just as it is verbatim. So I ended up rederiving the Schrodinger equation with different dimensionalities to what Schrodinger used, and it came up with some nonsense, but it was an interesting exercise, and I wanted to go and pursue that deeper because I didn't study theoretical physics, I was experimentalist, and I wanted to rederive everything from scratch using curvilinear coordinates, or at least have the capacity to understand the work that's previous work. The second motivation is I want to kind of, other than understanding nature better, I want to just be a wild goose, go for a wild goose chase and try to solve the mass gap problem, the Yang-Mills problem. And interesting approach that's different to just traditionally uh, coming up with a proof would be to create a kind of AI system which has been trained on a different formalism, a different programming language. This is something that George Hotz has been working on as a part-time project, similarly to me. He's called it Backspace AI, and it's a programming agent, and he's actually doing this. So, looking back at maths, and eventually going to be able to have a language where you can prove stuff in. And there might be a good reason why this isn't done. This isn't possible or difficult. But then, a step further, use that to train an AI system to on firstly proofs that we already know, and then find new proofs. I have a third motivation, which is I just want to get really good at fusion reactor engineering so that I can reconstruct all the phenomena and observations that scientists would need to make, and study. And you can do that all in virtual reality without a teacher, so it could be self-guided and very in-depth. Those are my motivations. Now I'm going to get on to problem 14. Show the maximum range of a projectile of fixed initial speed is obtained when it is launched at an angle of 45 degrees to the horizontal. Ignore the effects of air resistance. The initial speed of a bullet fired from a rifle is 630 meters per second. The rifle is fired at the center of a target 700 meters away, at the same level as the target. In order to hit the target, the rifle must be aimed at a point above the target. How far above the center of the target must the rifle be aimed? So another way to frame that question is, over 700 meters of distance, how much gravity affect the trajectory? What will the maximum height reached by the bullet along its? What will be the maximum height reached by the bullet along its trajectory? So if we imagine you're going to fire it, you're going to have a little angle, and it's going to make an arc because there's no air resistance. It's going to be parabolic, and then it's going to hit the target. Solution. Figure 5 shows the trajectory of the projectile described in Cartesian coordinates. If the projectile is launched at t equals 0 with speed v and angle theta to the horizontal, its x-coordinate in the horizontal direction at time t equals t is x equals v t cos theta. I'm going to read it all out first, and then we're going to go through my solution, which is the same. So we have this diagram, and its y component in the vertical direction is y equals vt sine theta minus half gt squared. So this is some kind of acceleration times the distance integrated. So yeah, acceleration time, sorry, not times the distance, times time would give you just this speed. Then you integrate that again over time, and that gives you a distance, which you can add on to the component, which we'll see. When the projectile strikes the ground, y equals 0, so t equals 2v theta over g. The range d is thus given by d equals v cos theta 2v sine theta over g. 2v squared sine theta cos theta over g. So that's subbing in one of the expressions. You subbed it in already. You subbed in t, and then you're using an identity, which we know is sine 2 theta equals 2 sine theta cos theta. So d equals v squared sine 2 cos 2 theta, divide g. Sine x takes its maximum value at x equals 90 degrees because it's because of the function, the wave-like nature of the sine function. The maximum range is achieved when 2 theta equals 90 degrees, so theta equals 45 as required. Figure 6 shows the trajectory of the rifle bullet. We've got the y coordinate, the x coordinate, d, with the target is at 700 meters. If there was no gravity and you fired it up, it would go straight, but we know it's going to go back down, and this is the max height, it will be in the middle. For the bullet, we require that d equals 700 meters when v equals 630 meters per second. Taking g to be 9.81 meters per second squared gives theta equals 0.496. There is another solution in the range theta less than 90 degrees more than 0 degrees, which is 89.5 degrees. Although this is physically valid, common sense suggests we would not aim at a rifle almost vertically in order to hit a target 700 meters away in a horizontal direction. Why not? The rifle must therefore be aimed at a point d tan theta equals 6.1 meters above the center target. Let's work out what it would be if you did it the other way. Okay, admittedly that would be pretty hard to estimate. So your target's there, and you're going to estimate your rifle to go 22,292 meters above it when it's 700 meters away. Let's not do that. The bullet attains a maximum height when delta y over delta t equals 0. Since that's when the direction of the y component velocity would be changing, although the speed would be changing as well. Since delta y over delta t equals v sine theta minus gt, this happens at time t equals v sine theta over g. Substituting this value of t into the expression for y gives y max v squared sine squared theta over 2g. And our substitution of our values for v, which was 630, and theta, which was 0.4 something, 496, gives y max equals 1.52 meters. So 1.52 meters. Let's go through writing all this out. So here's an interesting point that goes beyond the scope of the question, but I was curious, so I did it. We have a v as the bullet's leaving the nozzle to be a positive value, of course. That's velocity. In the question, we're talking about speed, really. And then the bullet actually travels for 1.112 seconds. So at the midpoint, that would be 0.556 seconds, ignoring relativistic effects. And the gradient of the line would be minus g because it is effectively decelerating, and the whole area under the curve is the thing we're talking about in terms of the up and down distance. So if you wanted a shortcut way, hack way of finding y max, you'd get that value for t, square it, times it by g, divide 2, and then half of that would be the y max distance, just because we know it's parabolic, there's no air resistance and things like that. But anyway, I digress. We start with v equals x over t, distance over time, and we're assuming the same for y, because there's one speed, even though we used v. And to find the x component, we need to get the first we need to rearrange this, and because we want a distance, and then just to get the x component of the distance traveled, we're going to set up this triangle, and we know that cos A is the adjacent over the hypotenuse, so that will give you just that component. I always just think of like a crocodile for cos, and then sine being the other one. And then we do the same for y, but we know that you would learn these equations, or you would look them up in the book, but just to have a physical picture, because I like that, you know that there's an acceleration times its time, that gives you a speed, then you integrate that over t, and over t as well, using that y equals mx plus c, equation of a straight line, and you end up here putting that in there. Once you have that expression for y, you set the constraint that the ground is at y equals 0. And then you rearrange that equation that you had, and you just find t. And you end up here. And then you put that into the expression that you got for x, the original one. And then you see this, mathematicians say c, the 2 sine theta cos theta, which means you can use an identity, which is that converts to that. And then because we know that I'll get it up quickly, the sine function looks like this. It looks like this. It means that the maximum it could be is 1, which means, and we can just see from that that would occur when the angle is theta, or what's inside the function, which is how you end up doing this and saying that the maximum would be theta equals 45. And then for the rest of the question, we want to do this. We want to input the value for where the target is. We want to input the speed of the nozzle velocity, and we want to input the gravitational acceleration, and we rearrange that to find theta. And there are 2 solutions for theta. If you're looking at that function sine of theta, you'd know that basically 90 minus this would also give you that answer, that crazy answer, the 22,000 meter one. But you put that in to tan theta, and then times that by where the target is. You come out with aim the gun 6.1 meters above the target. And then once you've done that, you say, okay, when it's at the peak, it's going to be just changing, so it's v equals 0, and then it's going to mean that the differential is equal to 0, which is the max speed. So you differentiate that original y expression, you end up here. Then you input the rearranged t, v sine theta over g. You put the theta in, and you put that t back inside the original equation for y, which you can say is y max, and you end up with this. That's a g.